Welcome to a lesson with Dr. Powell. Let's suppose that we have the following series, and we want to find out what the sum is, at least up to a certain extent, or at least get it within a certain tolerance range of what the actual sum is. Well, we can just start by looking at partial sums. Maybe we can just add up a few of the terms and see how, and maybe it's close to the full sum, right? I mean, depending on on how big the rest of the series is that we haven't added up. I mean, well, okay, so what if we just start? Maybe we can just plug in 2 e to the negative 2. We add the next one, e to the negative 3 plus 4 e to the negative 4, 5. And let's just stop. All right, let's see. How far off are we? Um, well, what we have left to add is this. What we haven't added is when n is 6 forever. Okay, we haven't added this. So maybe we can think about, um, remember how we could relate a series to an integral? So let's see, sorry, I forgot to write the e in there. So n times e to the negative n. So remember how we were talking about how a series, it relates to an integral. So it relates to it. We see how we are at 6, we go back to get more area. We go back to 5, and we look at this same thing with x replaced for n. And this integral is an upper bound for how far we're off. Let's see what that is. So if we did this, we did do a little integration by parts here. There's x1, 0, e to the negative x, negative e to the negative x, e to the negative x. So we end up getting plus and minus. We end up getting negative e to the negative x minus e to the negative x, going from 5, and a limit as x goes to infinity. So when x goes to infinity, this part right here will be, so I need an x here, right? I didn't get that in. When I multiplied x times that, I got an x, sorry. So that, but this part will go to 0. You need to use a L'Hopital's rule here in this limit, because that's like e to the x, and you get a 1 over e to the x with derivative of the top, derivative of the bottom, and that will go to 0. So this whole thing right here will go to 0 as x goes off to infinity. So really, you just have to plug in 5 and take the negative of that, which would make it all positive here. So really, we're looking at 5 e to the negative 5 plus e to the negative 5. Or in other words, we're looking at 6 times e to the negative 5. So 6 times e to the negative 5 is actually larger than what's left. I mean, and that's a fairly small number. If we let's see, that's e to the, so e is like about 2.7, say. So e is about 2.7 approximately, and you're raising it to the 5th power, and that's a 6. And if you want it, and you can type that in a calculator, whatever. But if you think about this, let's see, you could also say that even if you replace that with a 5 in there, okay, because 2.7 is to the 5th is bigger than 2 to the 5th, so you reverse the inequality for if in the denominator. So you can kind of think it's like 6 over 32. So yeah, like less than a fifth. So you're about less than a fifth off from the actual sum just by taking these first 4 terms that you're adding. So you see what we did. Let's kind of review what we did. What we did to find out how far we were off is we give a certain number of terms, right? We give a certain number of terms. Now the n where we stop, so we stopped at n is equal to 5. That's going to be right before the n where we start with the sum. So that's the n actually what we throw in the integral. So where we stop, we throw into the integral, and we integrate that, and that'll give an upper bound on what's left. This is true if we have a decreasing positive function. That's this is how we can get an upper bound for the remainder, what's left after we've added by so many things. Thanks for watching.